Okay, good evening. This is Professor David J. Delos Reyes. It's September 11, 2023. The time is 11:10 p.m. Okay. My topic for this session will be a long video format discussion on AC machines, and we are now on lesson number 8. So for those of you who are following my channel on the discussion alternating current machines, this will now be lesson number 8. Okay, let's proceed. The lesson for this evening will be alternating current machines, lesson number 8. Okay, we are running smooth. We are still on the study of transformer. Okay, transformer is an alternating current machine. That's the one giving us power to our homes. Okay, because without these transformers being energized by the power plants of utility companies, we don't have any power at home. Not unless you have your own do-it-yourself, maybe solar panel installation, right? Like me, I've got my solar panel installation. So much so with that. Okay. The title of the topic for tonight will be voltage and current relations. Okay. When the load power factor is unity. There is already a load on the secondary of the transformer. Lesson number 7. There is no load on the secondary side. There was no load connected over here. So we are now studying the relations of current and voltages if there is a load connected across the secondary. This CL here is actually households, right? It is represented by capital letter Z with the subscript L, meaning total impedance of a load. It's household, right? Or a business entity. Okay, let's try to bring out the relation of the current and voltage relations if the power factor is unity. Meaning, if the power factor is unity, it could be that the total load, okay, that is connected on the secondary are all lighting loads. Power factor of is unity, it's all lighting loads. Right? Under the study of AC circuit, okay, if the load is just a pure lighting load, it is to be considered a pure resistive load, right? So the power factor is unity, therefore power factor is actually equal to 1. What's the importance of power factor? Power factor is important because if you do not know the relation of power factor with respect to apparent power and true power, okay, there will be a problem. Because power factor by definition is actually true power over apparent power or some other formulas. Okay, I give formulas on how to compute power factor under the study of AC circuit. But the usual one, which is used under the study of transformer, is actually power factor is the ratio of true power over apparent power. That is capital letter P divided by capital letter S. Okay, let's proceed. So if the given load is actually a pure lighting load, okay, to get the relation, okay, we will start with the secondary portion. Secondary portion first. Okay. The voltage across the terminal is actually the one that's going, being taken to our service entrance, right? So, for us to take a value of 120 volts on the secondary, there should be an induced voltage on the secondary which is greater than this to obtain 120 volts. Okay, you got it? Why? Because there is the so-called RS and XS effects. RS is actually the internal impedance of the coil, and XS is actually an inductance of the coil. There is no such thing as a perfect coil. If there is a coil, there should be an X of L. It is actually termed to as X of L and R sub L. But the subscript here referred to secondary, but in reality, this resistance is actually RL, and this XS is actually XL, right? So to obtain 120 volts on the secondary, okay, we must have to take into consideration the effect of this, because as current passes through RS and XS, there should be a voltage drop, okay? And whatever the value of ES here minus that voltage drop will be that 120 volts. Okay, you got it? So the relation of the voltages and currents will be this formula here. That is, the induced voltage on the secondary should be equal to the terminal voltage here. The one going the one that goes to our houses, the so-called service entrance, plus the product of IS multiplied by the vector sum of RS plus JX of S. Vectorially. Okay? We could not just use the so-called real number operations. It's a complex operation. So AS will be equal to BS plus the product of IS times the quantity RS plus Gx of S. How is that so? Because the product of current times impedance is equal to voltage. So actually we are taking the summation of voltages here. That is, the induced voltage will be equal to the value of Bs, the one that appears out the terminal going to our service entrance, plus the product of the current, okay, that will be coming out due to this load, okay, times the vectorial sum of Rs plus G X of S. So this is actually the relation. Okay, with regards to the so-called vector diagram is just, at least we know how to graph this one vectorially. It is like this. Considering the secondary sides, so this is now the relation of the voltages and currents on the secondary side. If we try to draw the vector diagram, it is like this. The flux is erected upwards, the neutral flux, the one linking the primary and secondary. Okay, flux, neutral flux. It is like this. And B sub S is actually this line here. It goes horizontally, this one. The one marked with B sub S. And since the current is in phase with B sub S, why it is in phase? Because the load is lighting load, right? If it's a pure resistance, the current that will be drawn here, okay, has the same phase with the voltage that is coming out over here. That's why this is IS, this is BS, they are in phase. So meaning to say, if you try to take the graph, if this is the voltage, the current maybe it's still like this, okay? They are in phase. When the one goes up, the other one goes up. When the other one goes down, the other one goes down. Meaning they are in phase, right? But vectorially, this one could be represented as this is BS, and the smaller arrow is actually IS. Okay? Then we extend a little bit, and this will now be the product of ISRS. The voltage drop due to the resistance is actually in phase with B sub S. It is this. And the other component of the voltage drop is actually, it is not in phase, because this is X sub S is actually imaginary part. It goes up. Okay? So this is actually the product of I sub S and X sub S. So the vectorial sum of ISRS is actually the product of I times CS. It is this. Right? So if we try to add this BS here plus ISRS, okay, we add it vectorially with ISXS, this will now be ES. this biggest arrow, this one. And this ES here is actually this one. Okay? So this equation, this is just the vectorial representation. Okay? At least if you are an electrical engineer, if you got an equation, you know how to draw it and its equivalent in terms of vectorial representation. So this is the vectorial representation. The other representation is if you try to see these voltages and currents in the oscilloscope, it will be like this, right? This should be the voltage and this should be the current. They are in phase. When the voltage goes up, the current goes up. When the voltage goes down, the current goes down, meaning they are in phase, right? That is by using the oscilloscope. But vectorially speaking, this should be the representation. IS and BS is actually in phase. They are in the same direction. Okay? That's it. Or how could we determine now the current and voltage relations if we now try to go back to the primary? We have computed already the current, okay, considering a load that is a pure resistance with the unity power factor. So if we all repair these voltages and currents to the primary, we will be using the so-called transformation ratio, right? By definition, transformation ratio is actually the ratio of the induced voltage on the primary over the induced voltage on the secondary. So if we try to repair this ES here with respect to the primary, okay, it will be this equation here, right? And the other equation for taking the ratio of transformation, it is actually the ratio of IS over IP. Okay? So if we try to repair this IS here with respect to the primary, I primary will be the ratio IS over A. Okay? So all values here, okay, if we are considering voltage, it should be multiplied by A. And if we try to repair currents on the secondary, on the primary side, it should be divided by A. Kaya, so considering the primary side now, okay, the relation now will be this. This IS here is due to the pure resistance load, right? So what will be the corresponding value of IP if this value of IS is given? So for us to get the relation of IP with respect to this computed IS due to the pure resistance load, okay, we will repair all values to the primary side. So this value ES, if we try to repair it to the primary side, it will be this equation here. The computed value of IS, if we try to repair it on the primary side, it will be the ratio IS over A. Right? So if we now try to take the, if we now try to bring out the equation for the total primary current, okay, what will be the value of this due to IS? There is a value. Okay, let's try to do it like this. When there is no load, there is a current going in, right? And that is actually the current at no load. Current at no load is actually the current due to the effect of the core or the laminations. The one we discussed the last time around, the effect of the hysteresis and eddy current. But if there is a load, this I no load still exists, right? Whether we like it or not, there should be a value here. So the total primary current, when there is a load over here, it should be the no load current, okay, plus the current due to the load, which is IS. So we will add up IS, refer to the primary side, plus this. That will be the total primary current. So I place it here. The total primary current will be the no load current, okay? No load current is when the secondary of the transformer is open, right? But if there is a load, this no load current still exists, right? There is still effect of the laminations, okay? And the movement of the coil and the so-called flux with respect to each other. There is a loss for that one. we call it the so-called hysteresis in eddy current. So if there is a load, this IL no load still exists, plus, okay, we add up a certain value. And what is that certain value? It is the value of IS due to R if we try to refer it to the primary side. And it should be this value here. Negative IS over A. It is this. Why there is a negative? Because we are referring it to the primary side, right? If we try to draw this, this is IS, right? Originally. If we try to refer this to the primary side, we will reverse this one. Okay, we put it in the other direction. So we will be placing a value negative. Because if this direction is plus, the other direction should be minus. So this is now minus IS over A. You got it? Why there is a minus over here? Okay? And the vectorial sum of this minus IS over A, this one, we reverse this one. We put it in the other direction. The vectorial sum of this IS due to the load plus the current at no load, which is this. Current at no load is actually the vectorial sum of the hysteresis, which is upward, and the what you call this losses for the eddy current is actually the horizontal side. So the vectorial sum of these two components here is actually I no load. Right? So this is the current on the primary due to the effect of the secondary load, okay? If we try to take the sum of vectorial sum of this one and this one, that will be the total primary current. This one. Where is it? This one. Right? Then if we now try to draw the vector diagram, originally AS is actually on this side, right? This one. This one. If we try to reverse this one, if this is plus, the other side will be minus. So this voltage here will be the reverse of this one, right? We are taking the negative equivalent, so it is actually negative A times E sub S. If we try to return this to the primary side, it should be negative A times ES, right? So the vectorial sum of this EP here, the vectorial sum of this EP here, plus the effect of the impedance drop, which is RP plus GX sub P, actually represents B sub P. B sub P. Where is B sub P? B sub P, the applied voltage at the terminals. The one coming from the transmission line. So actually, with regards to voltages here, this is the highest one. This one here is higher than this one. Because we try to calculate going backwards, right? So whatever we computed here, we put it on the primary. So this is actually the highest voltage over here. So it is represented by this. This portion is the product of IP, RP. It is perpendicular to the value of IP, XP. So the vectorial sum of this negative voltage here, plus these two impedance drop, is actually, this is actually BP. BP is this one. The largest thing. Right? So this is the primary induced voltage due to the secondary load. This is the impedance drop for the resistance. This is for the reactance. So if we add vectorially these three things here, it represents BP. And this is represented by this formula here. Okay? The product IP, the total primary current, times the vectorial sum of RP plus J X of P. This is plus J X of P. That should be J. Okay? Plus the vectorial sum of negative A times ES is actually the total applied voltage on the primary. So the relation we are talking here is, this should be the relations, and this one. Plus these two here. So those are the relations considering that the load on the secondary is actually a pure resistance load. Okay, that's it, guys. At least we know how to represent an equation, and we could draw the vectorial representation of this, okay, on the board. Because if you know this one, but you do not know how to graph it, there's a problem. Because this equation here, this should be needed in the so-called voltage calculations of transmission lines. Okay? From the generator side to the load side, which is maybe 300 miles, okay, we will take into consideration the effect of the so-called resistance and inductance of the transmission line, right? We will take that into consideration also with transformer, right? Because without considering it, okay, the voltage that will be appearing at the far end will be, we could not predict the value. So to predict the value, okay, you take into consideration the effect of the so-called resistance and inductance effect. And there's other thing for what they call these transmission lines, the so-called capacitance effect to ground. Actually, there is a current from the transmission line going to ground, but we could not see it, right? But there is an effect of that one. There is a voltage drop due to that effect. Even the corona loss or something like that, it depends on the weather condition. There is effect on the voltage going that will be arriving at the parent. Okay, that's it, guys. So for those of you who are taking up electrical engineering, this is for you guys. If you want to subscribe to my channel is at youtube.com/@ProfDavidJDelosReyes. If you want to share it, please click share. Okay, good evening from Los Angeles, Professor David J. De Los Reyes.